If everybody could come, please. And if we could close the doors, please. All right. I want to welcome everybody. I'm Dick Lamers, chairman of the conference committee that organizes this, puts it on, and works all year to make sure that we have a good event for you. And it is just exciting to me to see the room filled. I know we've gone through some questionable times in the past, and our last active conference, I was working with KT the night before and saying, should we do this or not? And we did, and the world closed down the next day. So I am so glad everybody's here, and I'd like to start with Glenda Lee Rodriguez, who is the Provost and Vice Chancellor for Academic Affairs.
Good morning. Well, hi, everyone. It's my pleasure to welcome you to UW Stout. Can I get a show of hands? Anybody visiting Stout today for the first time? All right, welcome, welcome. And then how many of you have attended the conference before? Can I see a show of hands? Excellent. So no wonder the buzz in the room from just being able to connect with familiar faces. So thanks for coming. As Dick mentioned, my title is Provost. What does that mean? I oversee the academics here at the university. And so it's fantastic to see kids and people of all ages here because Stout is a really, really welcoming place. And we're what we call a polytechnic university. What does that mean? Well, it means we do three things and we try to do them really, really well. When we teach, we do applied learning. We want our students to get their hands dirty starting the first day that they're here on campus and really getting that applied experience. The second is that we have many, many programs that are really helping students set themselves up for careers across a diversity of different professions. And then the third one is collaboration. So today is just one example where we want to work with the community, with organizations, with K through 12, with other university partners to really do what we do best, which is problem solve and learn and bring skills together. I started at Stout in 2005. I'm a licensed architect, and I actually participated as a presenter in the very first conference with Cedar Core. We did a session on erosion. It was thrilling. I still remember it to this day. So it's just fun for me to now be back in this different capacity, but to really welcome you here. The last thing I just want to highlight is Stout, as I mentioned, has a lot of different programs that are all tied to water and water studies in some way. I'm going to just highlight some of them for you, especially for those middle schoolers and K through 12 folks here. Stout is a great place to come to school. We have biology and environmental science. At the master's level, we have conservation biology, so graduate studies. We have studies in sustainability, chemistry, and physics. Through our Discovery Center, our outreach arm, we have the Center for Limnological Research and Rehabilitation, working with, on solving community issues with water. Engineering and technology, we have programs, plastics and packaging, that are really looking at sustainability in those areas and how that impacts our environment. Food science technology, mathematics, statistics, computer science, psychology, social science, geography, sociology, anthropology. We have art and design programs too, really key players with aspects of design. And then Stout offers summer youth camps and outreach opportunities to get even learning done at a much earlier age. So thank you again for being here. I'm going to turn it right back over to Dick. But before I step away, I wanted to highlight someone in the crowd who'll be around for today, and that's Tamara Brantmeyer over there waving her hand. Tamara works in my office, but her role is to connect the community with our university and really encourage partner and student engagement activities. So if you have any questions about Stout and how to get connected with our students or our faculty and staff, many of them will be here today. Tina Lee and Nicole Hayes have a presentation about all the different water efforts that are going on at the university. But if you see Tamara, she's a great point person for you as well. So thanks again, and I really wish you a wonderful conference. Thank you, Dick.
Thank you. One thing she didn't ask, I'd like to ask, is how many of you are Stout alumni? We'll get some more. All right. So now I'd like to introduce a couple guests today. We've got Carol Olson and Kate Lucas. And I know I've got something here. There's Rod. Read the introduction that I have in there. Today's conference is in honor of Rod. He was my co-chair for 5 years and just a great guy in the community. Kate, could you say a few words about the River Docks Conservancy?
Hi, my name's Kate Lucas. I'm the naturalist educator for the River Dock Nature Conservancy. And the River Dock Nature Conservancy is a beautiful piece of land that's right on the Lake Desert, which is part of the Red Cedar River watershed. And 55 acres was donated by Dr. Rod Olson and Carol Olson to the Rice Lake Area School District in order for students to continue hands-on learning and learning outside about environmental and conservation education. So I've had the privilege of starting to build this program starting in October. The land was donated in October of 2021. And then this October, we started getting students out to the Conservancy to connect to what they're already learning in school. So just this past week, yesterday and the day before, we've had 5th graders out learning about living systems and predator-prey relationships. And really all of this is only done because of the generous donation from the River Dock himself, Dr. Rod Olson. So it is a great honor to be here as well, honoring him and return back to the Red Cedar River Watershed Conference, which I've been at before, and grateful to be here again. So thank you all for being here.
Good. So in honor of Rod, if you look at the picture, that's the conceptual drawing of the building that they're going to have on Lake Desert. And that tree is something this conference is going to donate to them. Thanks. Thank you. All right. That's a tough part of the day. So now, our sponsors. We can't do this without the generous donation of, first of all, you coming, but all of our sponsors that we have throughout the room and outside. Again, our gold sponsors, Dunn County and City of Menominee, are on top of the list. But if you would, please stop by every one of them and say thank you and see what they do. And there's a game that we have today. As you saw in your packet, there's a bingo sheet. And if you walk through, have the person at the booth check yours off. And at the end of the day, we're going to have those bags set up in front of the gifts. And you'll be able to place your completed bingo card, hopefully you put your name on it, in those bags to be able to be drawn at the end of the day. You have to be in attendance to get that prize. The team. So if our team could please stand. We've got the people that put this together this year, and could I please have a great round of applause? They're the people in the blue, and they'll be around all day, and please ask them a lot of questions. Try and stump them. But they're here to help. They want to make sure that you have a good day, educational day, a fun day. All right. Keep me on track here. That's what I missed. There's the names. I'll leave it up for a second so that you can see everybody that has been working on the group. There's 13 of us. And again, I sure appreciate their help. So that's our brand, the Red Cedar, land, water, and people coming together. The Red Cedar, people you meet from around the county, from around the Northwest say, "Oh, you live on that green lake?" Yep. And then the land, water, and people in blue, a much more positive note to show that we are getting better. The results show it. We've been working on this now for a long time, not just the conference, but I want to pay, after this slide, specific attention to an organization. But the next piece, if you read in the brochure, I ask you to challenge yourself. So make sure you read the introduction in the program, something that you'll need to do yourself. We won't collect anything from you. We won't question you. But it's again to spur thought on how do we get better and how do we move together so that the people portion of this, we are a tiny piece of the roughly 95,000 people covering 10 parts of 10 counties in the watershed. So you've got to talk to each other, talk across the table today, meet new people, try and walk out of here today meeting at least one new person you didn't know before and find out what they do and how can you help. So that's the slide. So that's the part, I'm not going to dwell on that. That's why we work on this. But on the right-hand side, the organization, Tanner-Monoma Lake Improvement Association, received an award 2014 as one of the outstanding associations in the state of Wisconsin. Sorry to see we had to close the doors and fold the organization in the last year through no fault of the people that were running it at the time. But again, we need volunteers in different organizations. We need that spirit of people wanting to get better and help. So to all the people for over the 40 years, if any of you are here that were members of that organization, thank you for getting us to this point today. So I'm guilty of this. What I'm guilty of is that I probably spend more time on the water, on the ice, than I do in the summer. And people have unsolicited comments over the last couple of years about that. They say, "Oh, wouldn't it be nice if you saw as many people out on the water in the summer on Lake Monoma or Lake Tanner as you do see ice shacks out there in the winter?" So hopefully someday that'll be true. That's taken off my dock. Sometimes that's what Tanner looks like. It's beautiful. Can't beat it. That's why I'm here today. My granddaughters. Again, sunsets are gorgeous. It's water. You want to do things with people on. And that's, again, sunsets, and you want to feel good about what you're doing and go to bed at night knowing that you've done something to help the water. But no sleeping today, okay? Again, in the program, there's a critique sheet. We'd ask you to make sure that you're filling that out during the day so that you don't wait till the end of the day and say, oh, I don't have enough time, and throw it away. Please, after every session, take a look at it, jot a note or two. That way, at the end of the day, you can drop it in, and that really helps us. We analyze that data and look forward to helping us in the next year of how do we get better for the next program. All right, I think we're up to Dan Zur, who's going to introduce our first keynote speaker. Yeah, we're on track. Thanks, Dan.
And for Dick, he's been kind of the standard bearer for this group. Good morning, everybody. My name is Dan Zur. I'm a natural resource educator with UW Extension. I'm based at UW Eau Claire, but I do a lot of work over here in the Red Cedar watershed. And just a reminder, what we're sharing with you here, what we're bringing to you, what people are learning from us. This problem is not unique to the Red Cedar watershed. We have it bad here compared to some other places, but water quality issues are pretty common all over the state. And we've had the chance to learn from other people. Other people have had the chance to learn from us. We hope that you learned some things today. It's wonderful to have some students here today to learn what's happening and get an introduction into this kind of work. If you want some more information about some things happening in the Red Cedar watershed, there is a website. Actually, Extension hosts a website called the Red Cedar River Watershed. I don't want to give you the URL, the address for it, because it's really long and hard to remember. Just do a search on Google, Red Cedar River Watershed, Wisconsin. It'll be the first thing that comes up. It's a UW Extension website. You can find the watershed plan that we follow. Yeah, that was written 8 years ago now for this watershed to try to improve water quality and soil health in the watershed. You can find all kinds of research in there. You can find minutes from the Red Cedar Partnership meetings. You can find annual reports are in there. I'm sorry, the 2022 is not done yet. We'll get to that. But 2021 is in there and years past. So lots of good information on that website if you're interested. So thank you so much for being here. It feels so good to be back in person with everybody again. Our first speaker this morning is Dr. Jim Boulter. Dr. Boulter is a professor of chemistry and environmental studies at the University of Wisconsin-Eau Claire in the Department of Public Health and Environmental Studies. He holds a bachelor's degree from Pacific Lutheran University in chemistry with an emphasis in environmental studies. Completed his PhD in analytical chemistry with an emphasis in atmospheric science at the University of Colorado Boulder. He joined the UW Eau Claire Department of Chemistry faculty in 2004. Was appointed as the inaugural director of the Watershed Institute for Collaborative Environmental Studies from 2011 to 2017. He teaches classes across a broad range of topics, including general analytical and environmental chemistry, radiation, air pollution, climate change, and sustainability. His recent research activities are split between laboratory studies of atmospheric particulate matter related to climate and human health and public surveys in the U.S. and China, focused on perceptions of and responses to climate change. He's a member of the Wisconsin Institute for Climate Change Impacts in the Human Health Working Group. And if you've noticed, if you look through the schedule for today, climate change is kind of a subtopic of what we're talking about today, because it's very important to the kind of work we do. Larger rain events, more frequent large rain events are increasing the erosion issues that we have. Ice on and ice off has changed over the last half century or so. And that causes water quality issues. Algae have a shot at the sunlight sooner in the spring. and hang around later in the fall. So climate change is very important to all the things that we do. I want to welcome Jim, and let me say that my office is right next to Jim's on UW Eau Claire's campus, and I highly recommend, if you want to have like really interesting conversations about climate change, have an office next to an atmospheric scientist. It's very handy. So please join me in welcoming Jim. Jim is moving a little slow this morning, but he's coming up. Thank you.
Well, I'll just hold it. Good morning. First of all, thank you. Thank you to the organizers for asking me to be at this conference. It's nice to be here at UW Stout, my sister institution just down the road that I value. It's also fantastic to be here with all of you. I'm so honored to be here because as I look through the program, I look around the room here, I see so many people who represent so many areas of varied expertise and also so many stakeholders who are really passionate about this watershed and the natural environment, as well as that great intersection between humanity, water, air, and so I'm really pleased to be here. I also want to thank Dick Lamers in his opening for challenging us all. This is a time of great challenge. Certainly with regard to the watershed, but I'm going to be speaking about another challenge that, as Dan said, is closely related, which is the challenge of climate change. Where do humans and water and land all come together? They come together on the topic of agriculture. Agriculture depends on the water and the air and the soil, and human beings depend on agriculture and the water and the air. And so that's what is our topic for today. I'm going to start off by talking a little bit about the challenge ahead of us, how we got there, the situation we're in and how we got there. And then I'm going to talk about where we're going, where we're headed, what the trajectory is. That's all pretty sobering stuff. But what I want to then transition to is what is our response? And as an atmospheric scientist, as a chemist, I can tell you what the science tells us we need to accomplish, and in the time frame in which we need to accomplish it. But you out there many of you are subject matter experts on how we get there. And so I'm hoping that we'll have time at the end for maybe some questions and answers, and even an opportunity for a little bit of discussion about the proper paths to take. So Wisconsin is undergoing changes. Dan alluded to that earlier. Average temperatures rising, extreme heat events, precipitation pattern, droughts, floods, extreme weather events. Let's make that a little more specific though. I'm going to just first of all show you this slide here. There's a lot of text on it, but then I'm going to revisit that information with some data, right? So the last 2 decades have been the warmest on record, and the past decade has been the wettest for Wisconsin. Extreme weather has generally increased in frequency and in magnitude, and extreme weather includes obviously experience of extreme heat, also extreme cold, and deluges or high precipitation, also extreme winds. Heavy rains have been showing an increase over time, and I'll show you some data about that. Our average daily temperature has increased by about 3 degrees across the state since 1950. And what you'll see is that the warming is happening the most right here in the northwest part of the state, and incidentally most during the winter months, where the temperature changes maybe 4 to 6 degrees on average in Fahrenheit. Our precipitation is increased by about 17%. Our annual rainfall in the state of Wisconsin is about 34 or so inches per year, and we've already increased by about 5 inches per year. But what we're really seeing is the way the rain falls is different, and it's falling in heavier bursts. Although southern Wisconsin is experiencing the highest increase, we have had some catastrophic rainfalls also in the northern part of the state. So let's see what that looks like. Here we see on the left the historical change in annual temperature, and it's actually pretty homogeneous across the state. You see the state divided into these areas. This was done by the group Wiki, the Wisconsin Initiative on Climate Change Impacts. And anywhere you see a star, that says that the change that's being measured here is of statistical significance, right? And so you see that across the state, vast majority of the state is warming by about 3 degrees, has warmed by about 3 degrees since 1950 over the past 70 years. Annual precipitation, more in the south part of the state, a little less in the north part of the state, but between maybe as little as 5 to 10% in our watershed here. Let's dig a little deeper. As I said, we're seeing most of the warming occur really in the winter and at night. So why at night? If you think about it, as the greenhouse effect and as climate change exacerbates the greenhouse effect, what it does is it traps heat in specifically the heat emanating from the surface of the Earth in the infrared portion of the spectrum. And so it would make sense that we would disproportionately see the warming occur at night when the sun isn't shining and the Earth is radiating back to space. Our enhanced greenhouse due to human intervention is trapping it more effectively. So we see the nighttime warming being larger than the daytime warming, and incidentally more and more in the northwestern part of the state. In terms of precipitation changes, as I said, in the spring and in the summer, we're seeing increases in average annual precipitation, primarily in the southern part of the state. And in fact, in the summer, you're seeing the northwest part of the state, you're actually seeing a substantial decrease in precipitation, not statistically significant, but that's the trend. It's just harder to tell that from the noise, from the background variations. We are seeing increased precipitation in the winter. And we would think, especially those of you who are Berkey skiers, any Berkey skiers here, by the way? Berkebiner, okay, great. And that's been a concern, right? Not because we're getting more precipitation, but we're getting more precipitation when maybe it's abnormally warm. And so what we get is rain on top of the snow, and that's a problem for all sorts of the sort of activities that we want to take, that as Wisconsinites we want to take part in during the winter months, as well as the financial, the economic viability of places like Birchwood up in the northern portion of the watershed. So we're seeing increased precipitation in winter, but it's not always snow. In the right-hand side of the slide here, we see changes in observed annual precipitation. But if I go, and I should say that the bars are 5-year averages, and that makes it a little harder, a little easier to understand the trends. The dots and the skinny lines are the annual variations, which are averaged into the bars. And then the heavy line across the middle there is just the average, right? So that's not showing a trend at all. It's just the average over all years. But what we can see now is if we look at the number of days in which we had a precipitation event of 1 inch or more, we see a trend there really starting about 2000, most of the trend in 2000, a little bit through the second half of the century, but really accelerating once we hit about the year 2000. If we look at the number of days with precipitation events of 2 inches or more, again, the trend's a little weaker, but now we can see that there's definitely a trend starting about 1970 or so, and increasing as we're seeing more and more of these 2-inch precipitation events. And then finally, my 3-inch precipitation events isn't showing up. Okay, but you get the idea. Those are sort of what we call the climate drivers, right? Those are the sort of the fundamental ways in which a warmer, lower atmosphere, what we call the troposphere, manifests itself. We see increases in warm days. We also see, I didn't show the slide here, but we also see that the nighttime lows, the nighttime low temperatures in winter are getting warmer. And then that influences the precipitation. Why? Simply because a warmer air means faster evaporation. Additionally, The warmer atmosphere can hold more water vapor. So as that water vapor transits across a landscape before it condenses to form clouds, raindrops, and rain, it just means that there's more water to work with. And so we see these enhanced precipitation events and as we've seen there. So what we can do is we can take our understanding of what's gone before, we can put it into sophisticated computer models. And what we do is we take those computer models and we reference them back to historical data to test the models, to make sure that the models are working, that they have predictive power. And then we use those same models instead of looking backwards, backcasting, we then take those models and forecast. So what is coming down the pike? That is, what does our scientific understanding tell us about the increases in climate change over the coming years? Well, on the left-hand side of the slide there, you see the temperature variations from 1900 to about 2020, and then projecting forward, you see two lines, and it turns out, I'm going to look at these lines in a slightly different way. These are the exact same data here, but instead of having two lines, what I'm really presenting there in the red smudge and the green smudge is sort of the uncertainty in the computer model. And so we recognize that looking back, we see the gray smudge there that kind of establishes the range of expected variability, and then the green smudge and the red smudge show the expected range of variability too. So what's the difference between green and red? It turns the difference between green and red is what we as the human species do, right? That's dependent on our actions. Those are based on two possible sets of future emissions of human-caused greenhouse gases. We have a lower emissions and a higher emissions scenario. And I'll give you a little more detail on those in just a bit. But what I want you to show you is, I think it's actually easier to see in this slide here. If you look at 2050, and I can't laser point the screen right now, but if you look along the axis there to the year 2050, and then you go and follow that gray line up, you'll see the distance between the two lines is not that great. And 50, right? But if you go all the way to the end of the century, you see the distance between the lines is pretty substantial. And the reason I want to highlight that is because what that tells us is regardless of what human beings do, the next 25 to 30 years, we have a pretty good idea of what's going to happen, right? It's after that we see a large divergence that really indicates the magnitude of future change. Again, if you look at this line here, there's no line for you, but you go straight up from 2050, you see there's a substantial overlap between the red smudge and the green smudge, and that tells you that there's a high likelihood of consistent results, regardless of whether we're looking, regardless of human actions. And if we then project forward to the year 2050, now, I'm not telling you which scenario this is because I've just kind of told you that by 2050, there's not a real substantial difference between the two scenarios, right? So I'm just going to say we're going to project forward by 2050. And what do we see? And it's actually pretty consistent with what we've already seen, but a little bit more so, right? We see that in the northwest corner of Wisconsin, we see wintertime warming greater than other seasons, especially at the nighttime. And so we see the daytime temperatures increasing by about 5 degrees and nighttime temperatures by as much as 7 degrees Fahrenheit. Remember, that's over the next 25 to 30 years, right? The last 3 degrees of warming that we saw took place over 70. So what that really means is it's an acceleration of that temperature increase. We do see less warming in the southern parts of the state. And actually, one of the things that's kind of good news from this is we see less warming in the summer than the winter. Why is that good? Well, from a human health standpoint, that's good because extreme heat can cause a whole range of human health concerns. And so we're often concerned when we see more warming in the summer than in the winter. Warming in winter, as I'll talk about shortly, has other concerns, right? But that gives you sort of the magnitude of the shift that we're expecting. What about rainfall and precipitation in general? We anticipate most of the increase in precipitation to be in the winter and the spring. And incidentally, it's now noticed that it's more or less in the upper part of the state, the northern part of the state, where we're seeing a greater increase. And that increase in the winter is maybe another 10% or more, right? So I said over the last 70 years, we've seen about a 17% chance in the average annual precipitation. And over the coming decades, then we're looking for maybe another 10% increase, particularly in the winter and the spring months, a little less in the summer and the fall. It's also interesting to me, and this just comes out of the model, that we're seeing a larger increase in the northern part of the state, not in the southern part of the state, which has a higher, which has already shown a higher increase in precipitation over the past 70 years. So to sum it up, right, 2 to 8 degrees Fahrenheit above late century averages, a further increase by 2050 with emphasis in the winter and at night. The next thing I want to point out in the next slide is about sort of extreme conditions. So we'll look at extreme high temperatures, and we'll also look at extreme rainfall events. Let's look first of all at the top half on the left side of the slide. So this is now looking at the number of days during a typical year in which we have temperatures in excess of 90 degrees Fahrenheit. And as you look at the upper left-hand corner, you see historical, you see that typically in the southern part of the state, it's maybe 10 to 15 days above 90 degrees. And in the northern part of the state, it's closer to 5 to 10 days out of the year. As we look at towards 2050, we see the number of days of 90 degrees or more in the southern part of the state, maybe as high as 35 days above 90 degrees. And so you might wonder, how do we have such a dramatic increase? You know, I liken this to a baseball player. You have to kind of think back in baseball before there were good anti-doping regulations. But if you had a baseball player who was, what do you say, juicing, right? Taking steroids, what did it mean? Does it mean that every hit was that much harder? No, what it really meant is so you look at their home run average, right? If they're juicing, they're going to hit more home runs because each ball is going to travel just a little farther because each ball gets hit a little harder, right? And so what we're seeing here is those 90-degree days are kind of the home runs. And what we're really doing is sort of juicing the atmosphere, right? We're adding a steroid boost to the atmosphere in some sense. And so that's why we see that increase in extreme heat events. And granted, 90 degrees is extreme for Wisconsin. This is not the extreme temperature events that we're seeing around the world, days of 120, 130 Fahrenheit in other parts of the world. Let's look at rainfall frequency. Now, this is specifically of 2 inches or greater in a single day. And again, on the left bottom, you see historical, and you see that in the southern part of the state, as many as 12 to 14 days a year in which they got 2 inches of rainfall. A little less in the northern part of the state, and certainly a lot less as you get closer to Lake Michigan. Maybe just 2 to 4 days a year of extremely heavy rainfall events. But by 2050, we see a substantial increase, right? We see on the west side of the state, we're seeing the behavior that we saw really only before in the southern part of the state. So we see a substantial increase, particularly, right, if you look at how the patterns shift, you see most of the alteration occurring sort of in our part of the state, that sort of northwest corner. And so we're looking at very heavy rainfalls of 2 inches or more as a substantial increase. And I know some of you who are naturally attuned to issues of water, fertilizer runoff. That's what a lot of people here are concerned about, right? Those are the rainfall events in which you get enhanced runoff, not just of fertilizers and other nutrients, but also of soil, topsoil. Okay, so now I've laid out for you sort of the climatology, right? Those are things that we feel, but I think it's important when we're talking about climate change to make it a little more real, right? To bring it to the sort of the more specifics of our day-to-day activities. And consistent with the conference, I want to look at agriculture, surface water quality, and human health. There are a lot of things I could have looked at. For example, there's a wonderful presentation later today on the viability of brook trout. I'm not going to speak speak to that, but I'm very excited to hear that we have some DNR scientists here that can speak to that much more effectively than certainly than I could. And so I think there are many ecological changes that we're going to see here, but I'm not going to address those. I'm just going to limit it to agricultural surface water quality and human health. Having said that, right, there are a whole range of effects of climate change that are not rainfall and not temperature, and I haven't showed those most because of limitations of time. And this is just a map. This is from the Global Change Research Program in the federal government. This is a report they put out on the human health impacts of climate change back in 2016. And we see the kinds of effects that are really entering the news on sort of a weekly basis now. We see extreme precipitation events, we see flooding, inland flooding, we see sea level rise and hurricanes, we see even cold waves. Be happy to address that in the Q&A session. Why do we see extreme cold? But we see that also as a exacerbation due to especially warming at the polar regions, manifested down here in the continental United States. We see, of course, rising temperatures, heat waves, drought, and wildfires. And for each of those, you can imagine how they might affect our agriculture, our water, and our human health. Okay, so these are big bullet slides, and I apologize for that. I wish I had some pretty pictures to accompany these. But let me just talk you through a few of these. Warmer winters and wetter springs and increased rainfall events. How does that create hardships for Wisconsin farmers? Well, and some of you are farmers here, so I feel like I'm really preaching to the choir. And so maybe you can share your stories with me at the end, or with us at the end. But I mean, things that are pretty obvious, like waterlogged soils delay planting, and we've seen that. They harm water quality due to enhanced runoff of nutrients, either existing or fertilizer applied nutrients. Extreme heat for dairy farmers decreases milk production from dairy cows, and in very extreme events can actually cause premature mortality of dairy cattle and beef cattle. And then increased temperatures and also decreased rainfall events that we saw in the northwest part of the state projected forward require increased costs from irrigation water usage. Fortunately, unlike our fellow citizens in the western part of the United States, we haven't had to deal with the loss of water table yet here, like they have so catastrophically in the Central Valley of California. You know, those of you who are involved in soil conservation practices recognize that heavy rainfall events can actually compromise those. And we also have the issue of our snow cover is maybe not as good as, in terms of its insulating quality, is not as good as it used to be, and looking forward to the future because there's less snow. We're having melt events and even rainfall events on top of our snow. And then finally, we have these short-lived extreme cold periods. They're sometimes called polar vortexes, right? That are associated, and if they're associated with reduced snow cover, can cause damage to plants as well, with the extreme cold air not buffered by the snowfall. How about water? Oh dear, that font is small. Okay, so there's a lot of things that come from water, right? And we've talked about some of them already. These changing precipitation patterns can really harm water quality and alter aquatic ecosystems. You put that amount of nutrient loading in the water table, you get increased algal blooms. The die-off of those algal blooms causes biological oxygen demand, and what it does is it actually sucks up the oxygen from the water and makes a less hospitable environment for the fish to be in. It's also just the warmer temperatures may not be the right temperature range for a given species, and again, I encourage you to visit the Trout Talk to talk more about that. In some communities, we have combined stormwater and wastewater sewer systems, and in those cases, extreme rainfalls can flood the sewer systems, overwhelm the water treatment plant, and we get discharge of raw sewage into our riverways, and that's can lead to disease. It also leads to eutrophication and other concerns like that. And then interestingly, for people who aren't in municipal areas, extreme high rainfall events and flooding events can decrease the water quality in private drinking wells if it overtops the well casing, and we can get an introduction of microbes and other contaminants into the well itself. Dan mentioned this earlier, increasing variability on ice on and off dates alters the fish species that live in Wisconsin, in particular because it changes the thermal gradient in the lake, and so we can have increased fish kills due to lake stratification. And then finally, this is not an audience I need to say this to, right? Warmer temperatures contribute to algal blooms in addition to the nutrient loads I mentioned earlier. What about effects on people? Well, in some cases, it's on infrastructure, and that affects people because the infrastructure serves our society, and also the infrastructure is a substantial expense, right? And maintenance of that infrastructure requires taxpayer dollars. And so when we have these flood events, it can be deleterious to wastewater treatment plants, as I've said, but also to roads, bridges, and so forth. Heat-related illnesses, especially for those who are vulnerable, for the very young, the very old, those with underlying health conditions are more vulnerable to days of extreme heat. And as the region warms, it becomes less inhospitable to certain pest species, and I mean less inhospitable. That is the winter die-off of things like ticks. Means that we have a much longer tick season, and that increases the spread of diseases like Lyme and borreliosis and other tick-borne illnesses. And additionally, as we warm and become more moist, a little more of a tropical environment, we see certain species of mosquito that can carry West Nile virus. So those are some of the concerns. And of course, for animals who drink water contaminated by algae, and there's a great talk about this afternoon too, about the concerns of algae. That's human health, it's animal health, and so forth. I think I'll leave it there. Oh well, just let me say this last thing. When we have flooding events, inland flooding events, because rivers are at high levels, that can cause flooding of personal residences and businesses. And of course, as those are wet and we have high heat, that can lead to mold infestations and again, human health concerns, respiratory health risks, including asthma. And to summarize what I've said, but to put sort of this human health lens on it, extreme heat can lead to heat-related death and illnesses. Outdoor air quality can be impacted by forest fires, and some of you know this, right? So even when we have extreme forest fires in the west, we actually have decreased air quality here in Eau Claire. That soot from those smokes and from the smoke from the fires and the associated air pollutants actually make it all the way out here to Wisconsin. Flooding, contaminated water, disruptions to essential infrastructure. Vector-borne diseases like mosquitoes and ticks leading to those diseases. And then finally, I'll talk about this one, mental health and well-being. And this affects us all in different ways. Working at a college campus, as I talk with students, I recognize that climate stress is a real thing, that young people, and not just young people, are increasingly concerned about their future. I think back to Dick Lamer's poignant thoughts at the opening of this, and this is mental health and well-being is already a victim of climate change. But I also think about people who are adversely affected by the kinds of extreme weather events we've talked about. Farmers work so close to the margins, economically speaking, as it is, that the loss of a full season or even part of a season can lead to, emotional, to depression, and all sorts of things, right? The economic losses associated with the loss of a farm, the need to sell a farm are real. And so it's one of those things about climate change that we haven't talked about until very recently. But now mental health is really being discussed much more as it is affected by climate change. Okay, now that we're all thoroughly depressed, I've learned long ago that talking about climate change, you can't end there, right? You can't end with, oh my God, this is the situation we're in, this is where we're headed. We have to talk about, is it possible to respond? What responses do we need to make, and how are we going to get there? So I'm going to pivot now, and I'm going to talk about mitigation, adaptation, and resilience. And those are important terms in the climate world. Mitigation are those actions that we take to reduce the effects of future climate change. Most often that's things like reducing emissions of greenhouse gases. I gave a talk just last week in Eau Claire at the brand new L.E. Phillips Library. That library, by the way, is heated using ground source heat pumps. Some people call this geothermal. And so it's a great example of clean energy. And so I was really talking about how do we transition to the fossil fuel free economy? And that sounds like a ridiculous statement on the face of it. That in our lifetimes, in my lifetime, it's at least for sure, and certainly in their lifetimes, we have to say goodbye to fossil fuels forever. And that sounds like an incredibly impossible heavy lift. In some ways, what I'm going to talk about next, I think, is a greater challenge. So I again return to Dick Lamer's comments at the beginning about challenging ourselves. There is some challenge coming up in the next 15 or 20 minutes of this talk. So mitigation. It's moving away from combustion of fossil fuels and those emissions, but more challenging and more problematic, I think, is how do we reduce emissions from agriculture? Because those emissions are intrinsic to the process of doing agriculture. How do we adapt to the kinds of climate impacts that I've laid out to you, so that our societies are less affected by, so that we as individuals are less adversely affected by the kinds of climate changes that we've already seen and the additional ones that are coming down the pike. That means our infrastructure needs to change. It means that our social safety nets need to be solidified. And then in the middle, that sort of that two-circle Venn diagram, you see the things that address both mitigation and adaptation. They're water conservation, it's new energy systems, it's local food, it's education, it's building communities and strengthening communities, and it's things like planting urban forests, planting urban gardens. Excuse me. Okay. Well, if we're going to, I'm going to start with mitigation. And if we're going to mitigate, we have to know what we're mitigating. And there's no way around this. What we're mitigating is the emission of greenhouse gases. And the one most of us think about all the time is carbon dioxide, but it's not the only one, and it's not the only important one. And so here you see 10,000 years of carbon dioxide levels, so concentration of carbon dioxide in the atmosphere. And you see for the first 9,900 years, it was, not flat, certainly. We were coming out of an ice age at that time, so you see a slight increase from about 7,000 years to current day, but then you see the impacts of the Industrial Revolution. And the inset there look just from 1950 forward, and you see a steady and actually accelerating increase of carbon dioxide even to the current day. But it's not the only greenhouse gas. Methane is vitally important for ways I'll show you in a moment. And again, we're looking at 10,000 years of data there. The x-axis is coming, I promise. And so you see it fairly flat. What I want to point out is, while if you look at carbon dioxide, which increased from about 270 or 280 before the Industrial Revolution to about 420 now, we're about 50% higher than we were before the Industrial Revolution. But look at methane. Methane starts out before the Industrial Revolution about 600 or 700, and we're now about 16 or 1700. Methane is more than doubled in that same period of time. It has kind of an interesting shape too. If you look at the inset, it was rising, it kind of flattened out, and it's rising again. What's that about? The third gas that we're going to look at is nitrous oxide, N2O. And again, you can see that it was quite flat, extremely flat, actually. You see those little spikies on all the data points, and those are called error bars. And all that says is that talks about how sure we are of the number. There's so little nitrous oxide in the atmosphere that it's harder to measure, and so the uncertainty is a little higher. But what you can still see without looking too hard is there's a clear increase due to human activity. Okay, there's our three gases. And we're going to talk about those gases on the farm, right? First of all, I want to say that carbon dioxide on the farm comes from on-farm fossil fuel energy use, electricity use, and also not on the farm, but contributing to the farm is the production of nitrogen-based fertilizers. Methane really has three primary sources other than fossil fuel emissions. In the United States, fossil fuel emissions of methane is about 60%. Farm-related methane is about 40%. And those three primary sources are enteric fermentation in the gut of ruminants, manure, and also rice growing. In this country, we don't do a lot of rice growing, but on the international stage, rice growing is a pretty substantial methane source. And then nitrous oxide really comes from nitrogen-based fertilizers out of the soil. It's intrinsic to the soil chemistry, although it's exacerbated when there is excess nitrogen fertilizer applied, and also from manure. And if you look at those three, you see that approximately 3% of CO2 emissions come from the farm. So actually very little CO2 emissions come from the farm, but where we get agriculture really contributing substantially to national climate emissions is in methane, as I mentioned, primarily from livestock, and nitrous oxide primarily from fields, where it represents about 2/3 of total emissions. Now, they exist in the atmosphere at widely diverging quantities. If you look at carbon dioxide, it's about 0.04% of the atmosphere, not very much. Methane is only 0.5% of the amount of carbon dioxide, it's even less. And nitrous oxide is only less than 0.1% of the amount of carbon dioxide. So why are methane and nitrous oxide still important? It's because they're so much better at trapping that heat, the infrared radiation, the light that comes up from the surface of the Earth. They're better at trapping it. Over a 20-year time period, every molecule of methane is about 80 times better than carbon dioxide at trapping heat. And nitrous oxide is 273 times better at trapping heat than carbon dioxide. So in terms of their overall contributions to trapping heat, which is what we're concerned about, right? That's the first step in the process. Carbon dioxide is trapping about 66% of the heat, methane about 16% of the heat, and nitrous oxide about 6% of the heat that's being trapped, leading to a warming atmosphere. The last thing I want to point out, and it's kind of just put there as a sort of an afterthought, it's in that farthest right column, is how long these last in the atmosphere. And this becomes really important because carbon dioxide lasts in the atmosphere for at least a millennium, 1,000 years. Whereas nitrous oxide lasts for only about 100 years before it undergoes reaction and is lost to the atmosphere. And methane is a very short-lived gas. In that context, as greenhouse gases go, it only lasts for about 10 years. And so that's the other thing, as we start to think about mitigation, do we want to focus on long-term gases like carbon dioxide or short-term gases like methane? And you can actually make a pretty good argument, we're hearing it more and more, that actually we want to focus our short-term efforts on methane. Why? Because it's more bang for the buck, right? It has 81 times the heat trapping capacity of carbon dioxide. And so if we stop that now, in 10 years' time, we start to run out of methane and we start to see the atmosphere heat less. Now, we can't just focus on one, but that does build a case, the short lifetime of methane and its strong GWP, global warming potential. It gives a good indication of why that might be a good target to start with. How are we doing? Well, this is not looking at concentrations in the atmospheres. This is talking about the increase in the atmosphere every year. And you see that every decade, those are the horizontal black lines, is more concentrated than the previous decade. Methane is a funny story. Over time, we stopped emitting methane, and now we're emitting methane again. Why is that? Well, there's a couple reasons. A lot of that is oil field methane. It comes from hydrofracking, hydrofracturing oil deposits and gas deposits is probably some of it. Some of it is coming from natural sources, as we see thawing in the Arctic regions, and still other is coming from the fact that so much more of the world is eating more meat as the poorly developed parts of the world become more economically viable. They're consuming more meat and more cows. Nitrous oxide increases kind of steadily. Okay, so what is our response? What do we need to do? I can't tell you how to do it because that's your expertise, but I can tell you what needs to be done, and that is we need to reduce our emissions. And so here we have, this is from a United Nations document from the United Nations Framework Convention on Climate Change, their most recent report from 2022. And we see 5 different scenarios, not the 2 I showed you earlier, but here are 5 different scenarios, and these are emissions of carbon dioxide. And the 2 that I showed you earlier are more or less the top 2. In order to get where we need to go, we need to look at the bottom 3 scenarios. We also need to cut our nitrous oxide and our methane. And what difference do those make? Well, those 5 scenarios there, from top to bottom, this is the difference they make by the end of the century. Now I'm in degrees Celsius now, I apologize for that change. But if we follow the top, the highest worst case scenario, sort of business as usual, we see about 4.5 degrees Celsius warming. Remember, right now we're about 1.1 and we're already feeling the effects, right? But if we choose the middle, the yellow one there, we've limited our increase to maybe 3.6. That's an important number because that yellow scenario is what the nations of the world have more or less agreed to already in the Paris Climate Agreement, right? So if they hold true to their commitments, the top 2 scenarios are already wiped off the books. And I think that's very encouraging. Now, we don't know how to get to the yellow scenario yet, but that's what the commitments have been. Can we make it to the bottom 2 scenarios? The dark blue scenario means that we top out at about 2 degrees Celsius, and that was the Paris Climate Agreement. The light blue scenario says maybe 1.5 degrees Celsius by the end of the century, and that was the ambitious target for Paris. How are we going to get there? In order to get to the bottom scenario, that 1.5 degree, we have to zero out our emissions, zero out all emissions of greenhouse gases by 2050. That's fossil fuel, that's agriculture, that's all of it. And if we want to choose the 2 degree, we've got to 2070. Wow. Can we do it? Do we have the technology? Do we have the economic ability? Do we have the will? Well, I'm here to tell you that I have a high degree of confidence that we have the technology. We accomplish all of those things with the technology we have today. We don't need to invent new technology, yet nonetheless, we are inventing new technology all the time that make this more and more feasible. Do we have the economic ability? You know, it's going to cost a lot of money. And I would have said it was a lot of money until COVID happened, until we started spending literally trillions of dollars to cope with the pandemic. And suddenly the billions of dollars that will take to get to where we need to go don't sound so unmanageable. I told you I was giving a talk at the library just last week. And the other thing that I will say is if we make these ambitious targets, every model that I look at says that the economic payback for accomplishing them is positive. That is, if we make the initial investments, they pay for themselves and start giving you a return on your investment within the next 15 to 20 years. So what I'm telling you is not only does it make good climate sense, it makes good economic sense for those 2 targets there, as ambitious as they sound. And that's just the economics. That's before you consider how much better human health will be with less air pollution, how much better human happiness will be with community gardens and good food, access to good food. So there are many, many sort of side effects of taking these sort of actions that are beneficial, job creation and greater economic growth. Okay, so how does agriculture play a role in this? Well, if we look at Wisconsin's greenhouse gas emissions by economic sector, we see that agriculture in purple is about 18% of that. Of the agricultural emissions, we see that soil management is about 41% of that, enteric fermentation in blue is about 36% of that, and manure management is about another 21% of that. So most of this actually comes to enteric fermentation and manure management. And of that, in red, you see that most of that is dairy cattle, and in blue, beef cattle. The vast majority of that is from cows. About 10% of Wisconsin's greenhouse gas emissions are actually from cows. Another 7.6 of Wisconsin's emissions are from soil management. So then what do we do? Turns out the agricultural sector has a lot of emissions, but the good news is it means that there is so much that can be done. I mentioned fossil fuel emissions of methane. It's currently thought that about 75% of fossil fuel emissions of methane can be zeroed out, and the people who are emitting them will actually see a net profit. How can agriculture similarly benefit from these sorts of actions? And it's things like climate smart agriculture. And I'm not going to belabor this because so many of you are already doing the kinds of things that we're talking about here that can see increased productivity, enhanced resilience to climate change, and reduced emissions. And improved nutrition of the food that's grown and eaten. How about dairy emissions? That's trickier, but there are a lot of good ideas out there. Manure biogas digesters that capture and reduce emissions, and also create on-farm energy for heat and for electricity. Maybe some of you have heard about Cows on the Beach is the name of the paper, a red seaweed that if it's generated in enough quantity can be fed to cows as only 1% of their feed, yet can reduce 60% of the methane emissions from their gut. Extraordinary. Also, great pasture practices such as silvopasture, mixing trees and grazing areas, and grassland rehabilitation will have become a way that the grassland now sucks up substantial portions of the carbon, which actually mitigates the emission from the cattle. And then finally, the decisions that we make as a society about the amount of meat, protein, and dairy that we consume. Can we reduce it? Are there alternatives? How do we do all of that yet maintain the economic viability of our farmers and farmlands? So I'll end with this. All of these things cost money. And especially in the agriculture sector, that's a real problem because farmers work on such small margins. So many of you have heard of the Inflation Reduction Act, which was the largest climate bill to have been passed by the United States, actually the first comprehensive climate bill to be passed by the United States, but also the largest climate bill to actually have been passed by any country when you just look at it from the dollars and cents standpoint. And if we look at the numbers there, it shows us that we can reduce our emissions by 2030 by about 40% relative to 2020. And that's a very exciting, relative to 2005. And so that's very exciting. How can farmers benefit from this? Well, it's primarily focused on energy efficiency, on energy generation, but it turns out there's a lot of funding in there for farmers related to climate smart agriculture. And some of you will know these programs better than I: the Environmental Quality Incentives Program, the Regional Conservation Partnership Program, the Conservation Stewardship Program, the Agricultural Conservation Easement Program, and the Conservation Technical Assistance Program all received substantial funding. And that's exciting because, as I understand it, these are already vastly oversubscribed programs. So it gives them more funding to do the good work that people like you are already doing. So I think that's a good place to end. I'll say the agriculture sector plays a crucial and sometimes complex role in surface water quality and in climate change. It is a substantial source of greenhouse gas emissions, but at the same time has a huge opportunity to reduce emissions both by conservation tillage practices and livestock practices. So here's the question: how does reducing agricultural greenhouse gas emissions relate to the goals of reducing agricultural excess nutrient runoff? What are the trade-offs and what are the synergies? And then finally, I'll note that if you want to see the slides from my talk, I will post them on my university webpage. Just follow the link there, Google me, and you can access the slides to my talk. Thank you very much.
All right, we do have 5-6 minutes for questions. So we've got some people out there with microphones, maybe. Here's Randy. Yep. Here you go.
Yeah, I was wondering if weather within a season is moving, such as winter. I always thought the coldest time of the year around here was the first week of January. Now it seems to have moved back into the end of January or February. Same with snow. We get so much snow in February, it just dwarfs the other months.
That's a great question. I'll confess, I don't know the answer on the temperature thing. My guess is that the precipitation trends that I showed, you're saying, yeah, we're getting more and more snow into the springtime, right? And as we look forward, I think we see an increase in both winter and spring precipitation. How those are distributed across winter and spring, right? The data only divides into the four seasons. If we had the actual model results in front of us, we could say is if we didn't divide into 4 seasons, but we did it by month, we might see that same sort of shift, but maybe across. As for the temperature, the lowest part of the year, I don't know. That's a great question. I don't know the answer to that. Thank you.
What do you view as the potential for soil to absorb carbon on a large scale and do that as a sink versus the emission discussion?
It's tremendous. I mean, there's a huge possibility that if you look at the roots, we always look at forests. We look to forests and say, this is where we trap carbon. But the root system of a prairie, go down 10, 12, 15 feet, right? So, and apologies, I'm not a biologist. A biologist might correct me on that exact number. But yeah, if we get away from tilling, so we're not destroying the root systems, a tremendous amount of carbon is stored in the root systems of prairies. And I don't have the exact numbers in front of me. And it's worth noting too that ruminants and prairies have a really important relationship, right? The hoof action of ruminants and also the fertilizer that they leave behind are actually vital to the establishment of a healthy prairie ecosystem. And so certainly I'm not saying no more cows, right? It means, right, the ruminants and the prairie go together and collectively can actually lead to substantial carbon sinks.
So kind of right along those lines, like you had mentioned about eating less meat, but a lot of the science shows that animals that are on managed grazing areas are healthier for humans. And so although there's a lot of animals out there, managed animals on grasslands, so then and in a state where we're known for dairy, there is a conflict in that. And then how do you talk about that to get folks to come together instead of being decisive in those places?
That's an excellent question. So, and forgive my inexpertness on this, but I think that if we move from a meat production mindset that was more industrial, I think of the feedlots of Nebraska and Kansas, to more of the Wisconsin model, frankly, right, in which we have more ranging head of cattle, right? I don't know that we could support the nation's meat consumption because it's much more land intensive, right? It takes much more land than a feedlot operation, right? And so I don't know that we could support the level of meat consumption that we now have with the kinds of meat production model that you're describing there, which is very appealing, right? So I'm in agreement with you. I just don't know that we have the capacity to do that with the amount of rangeland available. And I'd love to know your thoughts on that, actually.
Just briefly, since you asked, I don't actually think it is more land intensive if you take into account the footprint of the cropland required to feed those cattle.
Thank you. I love the drawdown project because, and those of you who aren't familiar with it, I encourage you to Google it. One of the things, it's about 100 and some odd different ways of not only reaching net zero, but actually going below net zero to actually reduce the amount of carbon dioxide in the atmosphere. And all of it is based on existing technologies. The question is really of scale, and that's I like their analysis. I've used it. I've taught it in classes before. The question is, can you scale all of those things at the level they are? And what the other thing I like about it is it's not a single, right? There are people that say, you know, all you need to do is plant 1 trillion trees. And that's been shown by many people to not be true. What I like about drawdown is that everyone has a stake in the game, right? And there are so many ways that some of which are complementary and many of which require vastly different levels, types of expertise. I mean, and so it's, we say a silver buckshot as opposed to a silver bullet approach. So I'm a big fan of Project Drawdown. Yeah.
All right. Well, I think we're about out of time. So thank you all. Thanks, Jim. Okay.
Just asked to point out about the posters that are up at the front of the room. If people have a chance to take a look at them sometime today, these are all research by undergraduate students who participated in a research experience for undergraduate site that we've hosted on this campus since 2014. So just wanted to point that out. Sorry, Dan.
Thanks, Tina. Yeah, during the break, check out the posters, check out the vendors. The presentations, the breakout presentations will be room A and C, which are up here, and then the other rooms are downstairs. So we've got until 10:15. Thank you so much.